Our second video to introduce this unit is going to look at a skill set you may not have used for a little while, but that is actually quite vital to progressing in the course, and that skill set is how to balance equations. What I'm going to do in this video is I'm going to show you a couple of different strategies that you can employ to balance equations, because many of you will struggle trying to do it just by inspection when you first start out. However, your ultimate goal should be to eventually get to the point where you can just compare left side and right side without having to write a whole lot of extra things down. But in the meantime, having a strategy to do that is a really great idea. So this first strategy that I'm going to show you is infamously called the Gerber color method of balancing equations. And what I'm going to do is I'm going to use a couple of different colored type circles to represent the different types of atoms that are present in this particular chemical equation. So as I skim and scan through this equation, I notice that there are two types of elements present. There are phosphorus atoms and there are oxygen atoms. I'm going to allow phosphorus atoms to be represented by circles that look like this. And so a P4 molecule could be represented using circles, 4 of them all stuck together. And we won't concern ourselves right now with the type of bonding that's holding those together, whether it's ionic or covalent, but we'll just represent it on paper as some sort of connection by having them touch. On the right-hand side, we see that there are 2 phosphorus atoms in that compound, and so we'll illustrate them there, again touching to show that they are connected by some kind of chemical means. And then I'm going to use a different color to represent oxygen. And so there are no oxygens in P4, but there is an O2 molecule on the left-hand side that looks like that. And on the right-hand side, this molecule has 5 oxygens. And so what I will do is just make sure they all stick together as such. Right. Now, to balance the equation, I can't break up any of these groupings. I'm not going to change their composition anyway. The only thing I can do is I can clone them. So the first thing I notice is that there are 4 phosphorus atoms on the right-hand side, but there are only 4 on the left, but there are only 2 on the right. And so in order to increase the number to 4, I have to be able to clone this molecule. So I'm going to grab it right there and clone the entire thing, except that the other ones didn't come with it. So here we go, we'll clone those 2, there they are. And we clone the entire molecule. And now we have 4 phosphorus atoms, the ones with sort of the bullseye type of design. In doing so, however, I've increased the number of oxygens on the right-hand side so that there are 5 in this one and 5 in this one for a total of 10. Therefore, I have to have 10 on the left-hand side as well. And the only way that I can achieve 10 is through the cloning process. So I can clone this once, twice, 3 times, and 1 more time to get a grand total of the 10 oxygens I need to balance with the 10 that are on the right. And so you can see now from a color perspective that the quantity of each type of sphere on each side is now equal. To summarize how many of each type of grouping we needed in order to balance the equation, we're going to put some coefficients or numbers in front of each type of molecule in the reaction equation. So up top here, I only used 1 P4. However, it's optional whether I put the 1 in there or not. For if there is no 1, it's assumed to be 1. For the oxygens, you can see that I used a total of 5 of those little O2 groupings to make the equation balanced. And on the right-hand side, I used a grand total of 2 of those P2O5 bundles to balance the equation. And that's how you can balance equations using the color method. The other example that I like to, or other strategy I'd like to show you through this example is a method just simply called left side, right side, or the inventory method. So on the left side of the equation and the right side of the equation, I have the same types of atoms, but they're in different arrangements. I'm going to begin by starting here with the very first element and listing it. And I'm just going to read across from left to right until I stop where the reactants end. So I have 4 carbons to start. I have 8 hydrogens to start, and I have 2 oxygens to start, all on the left-hand side of the equation. On the right-hand side, what I'm going to do is I'm actually going to list those elements in the exact same order, C, H, and O, even though their placement in the equation might be different. And the reason I want to do that is because I want to be able to compare quantities easily at a glance by looking across rows to see if they're the same or different. If I mix up the order, then my eye has to wander a little bit more to try and make that comparison. So when I look at the right-hand side of the equation, I see that I only have one carbon in the carbon dioxide molecule. I have two hydrogens in total solely from the water molecule. But the oxygens are found in two locations. They're found in the CO2 molecule and in the water molecule. You can see that I have 2 in CO2, 1 in water for a grand total of 3. So to balance this equation, we're going to try and make left side equal right side. If I begin with carbons, I notice there's 4 on the left, 1 on the right. I need to increase the right side to a total of 4, and I can only do that through cloning processes. So I'm going to have to multiply this carbon dioxide molecule by 4 in order to get 4 carbons. This 4 multiplies by the carbon and the oxygen in that molecule. So I now have my 4 carbons, but my oxygen count has changed because now in the CO2 part of the equation, I have 4 times 2 or 4 bundles of CO2s, which means I have 8 oxygens here, still have 1 here for a grand total of 9. Now, that makes carbon happy. It's balanced. Let's take a look at hydrogen. On the left side, I have 8. On the right side, I have 2. Is there something I could multiply this water by in order to get 8? Well, sure there is. I could multiply it by 4. But remember that that multiplication of 4 applies to both the H and the O because they're all in the same bundle. It's like cloning that water 3 more times to have a total of 4 waters. So I now have 8 hydrogens. But if I look at my oxygen total, I can see again that I have 8 that's in that carbon dioxide part of the equation, and 4 times 1, which is 4 over here, for a grand total of 12 oxygens. So I'm getting closer. I've got 2 of the 3 types of atoms balanced. The last one I have to balance is oxygen, which is great because in the chemical equation, I have it here as an element. And elements that are in an equation there and by themselves are best to leave to the very end because it gives you more flexibility in terms of what number can go in front of them. It won't have an impact on other types of atoms too. So I have 12 on the right and 2 on the left. Is there something I could multiply that oxygen by to get 12? Well, sure. I could clone it 5 more times to get a grand total of 6 of those oxygen pairings. And that will increase my oxygens to 12, which means that my equation is happily balanced on both sides. So a different approach, but it still yields you the same result in obtaining a perfectly balanced equation. For the final example in this video, I'd like you to pause it after you've written down, well actually pause it to write down the chemical equation, and then I'd like you to try either method. Try either the color method or the left side, right side method, or even if you're brave, try and do this one by inspection, meaning writing nothing down but just comparing each type of element back and forth to see if you can get it to balance. After you've paused it and tried it, then you can unpause and check your answers. I will do both the color method and I will do the left side, right side method. Pause now. Okay, I've set up the first way of solving it using the color method, and there's a little legend on the left-hand side to show you all the different colors that are used for the different types of elements. They're pretty wonky. You can keep yours a little simpler, but it's kind of fun to use some of the features of the smartboard too. So you can see that my Na2O molecule right here is pretty simple, 2 NAs and an O. My NH4 twice is equal to, this little bundle. There's an NH4 and there's an NH4 bundle. 1 sulfur and 4 oxygens is represented by that conglomerate of things. Let me give that back. Here we go. And my Na2SO4, again, pretty straightforward. 2 sodiums, a sulfur, 4 oxygens, the water, and the NH3. So when I do this by inspection by colors, I usually again start from left to right just because it's easy and conventional. So I notice that I have 2 sodiums on this side and I have 2 sodiums on this side. So they are balanced. And I'm just going to mark a little check mark there to indicate that so I don't lose track of where I am. Now the next element that's kind of listed is oxygen. Now, one of the problems with trying to balance oxygen right now is it's here, it's here, it's here, and it's here. It's in too many places. So I'm actually going to choose to leave oxygen until the very end, because if everything else balances, by default it will have to as well. So then going down the list, I have nitrogens. And you can see that I have 2 nitrogens here, but only 1 on this side right here. So that means I'm going to have to clone NH3. So let's see if we can get it all put together here. There it is. And we'll clone it too. There we go. So now I have 2 nitrogen atoms, 1 there and 1 there. So they are now equal on both sides. If I take a moment now and look at hydrogens, I can see that on the left-hand side, I have a grand total of 8 of them right here, all in that little bundle. And if I go to the right side, I can see that I have 2 here and 3 here for a grand total of 8. So 8 and 8 is great, means that they are balanced. Let's take a look also now at sulfur. Sulfur is represented by stars, and you can see pretty clearly there's only 1 on each side, so they too are balanced. So by default, if all 4 of these elements are balanced, the oxygens in theory should be 2. So let's check. We have 1 here and 4 here for a grand total of 5 on this side, and on the right side we have 4 here and 1 here for a grand total of 5 on this side. So we're done. We know that everything's balanced. And actually, this one that looked pretty ugly ended up being pretty simple because it only took 1 Na2O, 1 NH4 taken twice sulfate, 1 Na2SO4, 1 water, and the only number we actually have to write in is a 2 in front of NH3. So if you found that that started to get a little messy using all those colors, you're kind of right, because it's hard to keep track of, 5 different types of elements. So would the left side, right side approach work a little bit better if we tried it instead? I've actually set up the left side, right side approach for you by reading through the different types of elements from left to right and listing them from top to bottom. And you'll notice that I matched that list on this side as well, exact same orders. So again, I can compare across rows to see if the numbers are equal. So you can see that there are 2 sodiums in both cases, so they're already balanced. The oxygens are already balanced. The sulfurs are already balanced, and so it's only the nitrogens and hydrogens that are not. So I look at the nitrogen, I say there's 2 on the left, but there's only 1 on the right. What can I multiply the nitrogen by? And by multiply, I mean out in front. I can't change anything inside the chemical formula. It alters what's connected to what. So I can multiply it through by 2. And of course, when I do that, 2 times 1 will now give me a total of 2 nitrogens, and 2 times 3 there will give me 6. But there are 2 hydrogens also in the reaction equation on the right from water as well. So that's going to give me a grand total of 8 instead, which is an awesome thing because now everything's balanced. So when you compare and contrast the 2 methods using this example, you can see the pros and cons of both. The color method works maybe for some smaller types of reactions where there aren't so many types of elements to think of, but the left side, right side is a little faster, and you may even get to the point where you don't need to do the initial inventory. You can use it sort of as a summative inventory as you try to learn to balance just simply by inspection, by looking at it and doing it. Hopefully this gives you some tips and tricks on how to balance equations.